Well, today we get to start a new chapter, which means that in some sense it's a little easier. It doesn't compound the old information, but on the other hand, it's something new. Here's the concept. I want to motivate this by reviewing what you did in Calculus 1. In Calculus 1, you did a definite integral for a function of one variable. Today, we want to do a definite integral for a function of two variables, and then you can see naturally how to extend it to more than two variables, hopefully at the end. Here's the Calculus 1 problem. Suppose I wanted to find the area under a curve y equals f of x. That's kind of a difficult concept if you really think about it. Newton and Leibniz, with Newton first and Leibniz independently shortly thereafter, were just brilliant to be able to figure this out. How can I estimate the area below this curve as shown? Y equals f of x. Well, I could think of taking the interval over which I want the area, x equals a to x equals b, and break it up into n subintervals, we said, right? So I'll call it a, x0, and then the next point will be x1, next point x2, x3, all the way up to xn equal b, n subintervals. And then the width of each one, like delta xn, will be the width of the last one. So it's xn minus 1, the width of the last one. Delta x1 here is x1 minus x0. Delta x2 is x2 minus x1. This is just short notation for subtracting the endpoints to get the width of each interval. If the width of the kth interval is delta xk, and I pick any point whatsoever in the middle, like here's x3, the third interval, I'll choose some point, I'll call it x3 star, and I'll take the height of the function at that intermediate point, f of xk star, there it is. Then the area of the kth rectangle, if I add all these rectangles to estimate areas to estimate the area under the curve, is f of xk star, the height, times delta xk, the base width. Right? Base times height is the area of the rectangle. Then I add those, k equals 1 to n, I take height times base of the first rectangle, right? Height times the base of the second rectangle. F of x3 star is the height of the third one times delta x3, the base of the third one. Add all those together, I get an estimated area under the curve. And then you think, well, maybe I could get a better estimate if I made these rectangles smaller and smaller. Like, I mean, I'm very narrow, maybe I'd get a very good estimate. You would draw pictures and often see that, yeah, it looks like a better estimate, right? What you could do is consider taking the limit as n, the number of rectangles goes to infinity of the sum k equals 1 to n, height times base, right? And say, maybe that'll give me a really good estimate. Well, here's the brilliance of the calculus of Newton and Leibniz, is that if you take the limit as n goes to infinity with the width of the widest subinterval going to 0 and choose any intermediate points xk star whatsoever, some functions called integrable functions get the same limit no matter what. Isn't that great? That makes this sort of a significant quantity. If for a function you get the same limit no matter how you partition the interval, as long as the width of the widest subinterval goes to 0, and no matter what intermediate points you pick, you get the same number for the limit of the sum of the area of the rectangles. That's significant in the following sense. For instance, suppose I used circumscribed rectangles. I took on the last interval the height at the right endpoint, so I overestimated the area under the curve on the last interval. And same thing on every other interval. I take right endpoint, so in every interval I overestimate the area under the curve. We call those circumscribed rectangles. Then the sum of the rectangles ought to overestimate what I want to call the area under the curve, right? So I could take inscribed rectangles. For this function, I take the left endpoint of each interval, right? And I take the height right there at the left endpoint. And then each area of the rectangle, I ought to say, underestimates the area in that interval. And if I add up the areas of the n rectangles with inscribed rectangles, I get an underestimate. But here, if I have a function that's integrable, so that this limit is the same no matter how I break it up, then the limit of the area of the circumscribing rectangles and the limit of the area of the inscribed rectangles is the same, which means I ought to define this to be the area under the curve. So any function for which this limit exists, regardless of partition, implicit in this limit n goes to infinity means the width of the widest interval goes to 0. Sometimes I'll write limit width of the partition goes to 0 instead of this. You'll see different notations here. But those functions for which this is the same number, so that the inscribed and circumscribed rectangles give you the same limit, we'll call integrable functions, and we'll say this notation, integral a to b f of x dx, called the definite integral, will mean the limit of the sum f of x k star delta x k, delta x k. Furthermore, if f is not negative, that's what we want to call the area under the curve. So we'll say that area under the curve is actually equal to the definite integral when f is also not negative. Turns out there's a huge class of important functions for which that are integrable, the continuous functions. There's some others like piecewise continuous functions. But if I can draw that function with a single stroke of the pen on the interval so that it's continuous, then always the function is integrable. The limit of the sum is exactly the same number no matter how you break it up. And so this definite integral is this. We'll say all continuous functions are integrable. And for non-negative ones, this is the area under the curve. Why do I say non-negative? It's because if you have that function down here below the x-axis, say down here somewhere, and you take this f of x k star as negative times the base. So this is minus the height times the base. Then you're adding up minus the rectangle areas. And the integral, maybe you remember this from calculus 1, of a negative function on the interval gives you minus the area below the curve, below the x-axis and over the curve instead of plus the area below the curve. So for a negative function, this gives you minus area instead of area. It gives you minus the area above the curve. The area is always non-negative, but the definite integral might be negative when f is negative because it's giving you minus the area below the x-axis. So that was the concept. We said an function f of x of one variable is integrable if this limit is the same regardless. And if all continuous functions are integrable is a huge theorem. And if the function is non-negative, then we'll say that's the area under the curve and over the interval AB. All right. Also over on this one right here, we'll call that a Riemann sum after the famous mathematician Riemann. Probably would have been super brilliant. I mean, his name is on a lot of stuff. You don't know, maybe he was a student of the great Gauss, one of the three greatest mathematicians of all time, right? Gaussian this, Gaussian that, as you go through mathematics. Along with Newton and Archimedes, those are considered the three greatest. I think Riemann might have been one of the greatest too. He apparently hugely impressed Gauss, his advisor, when he presented his I think it was his dissertation, anyway, his paper. And that's hard to do, right? Impress Gauss. But last he got tuberculosis, which in those cases was a killer, right? He died, I think, at 39, so he didn't get very far along before his career was ended. But this is named, the sum on the left here is called a Riemann sum, f of x k star delta x k sum k equals 1 to n. And then the limit of the Riemann sum is what we call the definite integral. Now to calculus 3, after all that bantering about here, calculus 3, we're going to say, now what do we do with a function of two variables? Z equals f of x, y. Suppose for simplicity, it's over a rectangle in the xy plane here. This notation is new. It might throw you. What does that mean? You know what this means? AB with the closed braces means x between A and B inclusive. A less than or equal to x less than or equal to B. This one means y between C and D inclusive. C less than or equal to y less than or equal to D. And this is the Cartesian product. So it's all ordered pairs where x comes from this interval and y comes from this interval. It's just the rectangle, x between A and B and y between C and D. That's all it is. All right, so when you see that, don't get thrown. Suppose I partition a rectangle, because after all, now if I'm talking about a surface, here's how we sketch it. Z equals f of x, y is a surface. Maybe it's over a rectangle, x going from A to B, and y going from C to D over here. So it's this rectangle down here beneath the surface. If we have a function defined over a rectangle, here's the surface plot, z equals f of x, y, and suppose it's non-negative. I want to find the volume below a surface that's a function of two variables instead of the area below a curve that's a function of one variable. I could think of an analogous thing. I could add up all these little subvolumes of what we call rectangular parallelepipeds. Right, a parallelepiped is a six-sided figure with six parallelogram sides. And so rectangular parallelepiped is just a rectangular box like this. So here's one of the boxes underneath here. And suppose we partition x up into intervals just like before in calculus 1, delta x1, delta x2, delta x3, up to delta xn, m, capital M this time, subintervals. And we partition y into capital N subintervals, 1, 2, 3, up to capital N. Then there's m times n equals little n total rectangles in the xy plane. And we can put one of these rectangular boxes over each subrectangle of the rectangular region, the xy plane, and add up all these little sub-volumes to estimate the volume of the surface, right? And we can do exactly the same thing as in calculus 1. We can use circumscribed volume rectangular boxes, taking the highest point of over the jkth little rectangle down below, or we use inscribed, taking the lowest height of a point over the jkth rectangle. Here's the Riemann sum for a function of two variables. Sum j equals 1 to m, the number of increments in the x direction. Sum k equals 1 to n, the number of increments in the y direction. F of x j star, y k star, delta x j, the width of the j x interval, delta y k, the width of the k y interval. Sometimes you'll see this different notation. Sometimes I'll only put one sum here. The idea is you can also index these such that you just have one index, and the one index runs over all m times n boxes. So it means the same thing. I think it's easier to double index this, but sometimes I'll put one sum. In any case, you take the limit as little n, the number of total boxes, total rectangles on the xy plane goes to infinity, with the width in both the x and y direction going to 0 tacitly assumed. Of this double sum, where you're adding height times base times width times length, that gives you the volume of this jkth, I should say, subsolid. You take delta xj in this direction, delta yk in this direction, at any intermediate point whatsoever, xj star, xk star, you take the height up to the surface. And you get this volume that has this length times width times height, and there it is, height times length times width. The volume of the jkth sub-rectangular box, summed over all sub-rectangular boxes, estimates, I should put V instead of A, estimates V, the volume under the surface. Well, just as before, there's a wonderful theorem. If f is a continuous function of two variables, then the limit of that Riemann sum of two variables is the same no matter how you pick the points xj star, yk star in each rectangle. No matter how you break up the partition, as long as the width in both the x and y direction is going to 0 as the number of rectangles to infinity, you get the same number for the continuous functions and almost continuous functions. Some other ones, they can break into pieces, for instance. Since that's a significant quantity, you get the same number no matter what, and you can circumscribe and inscribe and get the same number. We ought to call that the volume below the surface, just because it's the limit coming from down and above and below, regardless. So we'll define this to be the definite integral. So we'll say this double integral sign r, f of x, y, dA means the limit of the sum. Just like in calculus 1, if you wrote the definite integral a to b, f of x dx, it meant the limit of the sum. This is the definition. That's why I put the def up there, of the double integral. And when f is continuous, this exists, it's integrable, and we'll call it the volume V should be here under the surface when f is also non-negative. Otherwise, if f is negative, then you have the same problem you did before. If the surface is below the xy plane, then this is a negative minus the height times the length times the width, and then you get minus the volume above the surface instead of plus the volume below. So there it is. By definition, we'll say this notation means the limit of this double sum, and when it exists, we'll say the function is integrable. All continuous functions are integrable, and any integrable function that's not negative, we'll say the volume is equal to this double. But now we have the same problem we had in calculus 1. Alas, how do you evaluate this terrible limit of the sum? It's just awful. Anybody ever try to do that in calculus 1? You almost did it for no examples at all. It's so hard. Yeah.
I was thinking I would like understand what the sum and then the next sum mean next to each other.
Yeah, it means the sum of the sums. It means you do the sum on the inside, j equals 1 to m, and then for each one of those with k fixed, and then for each one of those you do the sum on you sum the number you get on the inside over the outside. So what you're doing is you're taking in box 1 here, you're taking the volume of this rectangular box here plus the volume of this rectangular box plus the volume of this rectangular box plus the volume of this rectangular box for the inside sum when k equals 1. Then you take the second row of boxes when k equals 2, the third row of boxes when k equals 3, and you sum up. So the first one is over all these boxes in in the first row, and the k equals 2 is over all the boxes in the second row all the way down to the end. So we have m times n total rectangular box volumes or something. Then take the limit of the number of boxes goes to infinity with the width in both directions going to 0 will be the definite integral of function of two variables. Any other questions? This is the concept. This is where you have an advantage over the science majors who apply these formulas blindly and never know if they work. If you understand what's going on here, then when they get some funky surface that's not continuous, and they say, why am I getting different values for the sum? Well, it's not continuous. The theorem doesn't apply. So there's what we'll do. So I'll just restate this then. Whether or not f is, let me move this. Remember, just a little video is not good. That's a little better. Whether or not f is non-negative, we'll just call that in calculus 1. We'll say that the notation definite integral here, a to b, means the limit of the sum, right? And similarly in calculus 3, when we put the double integral over r f of x, y, dA, that means the limit of this sum, right? Where we're going over a rectangle r, which x goes from a to b and y goes from c to d. All right. And then this theorem, we said if f is continuous, then it's integrable. Leads to these additional theorems. Maybe I should write these down separately. It turns out in this that when f is integrable, the integral of the sum is the sum of the integrals for functions of two variables too. Let's just switch this over just for a second. So I'll make this note. Just as in calculus 1, when you took the integral of the sum was the sum of the integrals, you can pull a constant out. Similarly in calculus 2, if you take a double integral of a constant times f of xy plus a constant times g of xy dA over a rectangle, the integral of the sum is the sum of the integrals, and you can pull the constant out. So I can pull the c1 out and integrate f of xy dA, and I can pull the c2 out and integrate g of xy dA, provided that they're both integrable. So the integral of the sum is the sum of the integrals, and you can pull the constants out for f and g integrable. In other words, these individual integrals exist. And then it follows, since c's can be negative, that the integral of the difference is also the difference of the integrals. All right, so that's an important theorem there. I'm going to come back to this page in a minute if you didn't get that. But I want to put up the big theorem. It's the magic by which we actually evaluate these things. It's Fubini's theorem. It's like Houdini, Fubini, right? Magic. Suppose I need to evaluate this terrible limit of the sum. I got this mess. What did we do in calculus 1 to integrate when we couldn't evaluate the integral, the definite integral, which is defined to be a limit of a sum? You better put this back for a second. And what do we do? In calculus 1, if we had the integral from a to b of f of x dx, and f had an antiderivative, we could rewrite, which is true for all continuous functions, for instance, we could evaluate it by taking the antiderivative. This indefinite integral means an arbitrary antiderivative. This one means the limit of the sum. This one means an arbitrary antiderivative. We could take an arbitrary antiderivative, plug in b and a, and take the difference. You could also write this as f of b minus f of a is another way to write it. Maybe more familiar. But this relationship between the definite integral, that's the limit of the sum, and the antiderivative was Newton's and Leibniz's genius to be able to evaluate these things easily, right? If I want to integrate x squared dx, the area under a parabola, how can I do that? That's not so easy, right? Limit of a terrible sum. All I got to do is take the antiderivative. Say this goes from 0 to 1. 0 to 1. Here's the area under the parabola from 0 to 1 is x cubed over 3. Evaluate 1 and 0, take the difference, is 1/3 minus 0 is 1/3. We get an exact result because we can just do it with antiderivatives instead of evaluating the definition. So that was the calculus 1 brilliance. We could not use that definition. We could use this fundamental theorem of calculus. It comes in 2 parts. This is one part of it. One part of the fundamental theorem of calculus says use antiderivatives. It's easier, right? Now, what are we going to do for these double integrals? Let's put this back. There it is, Fubini's theorem. If f of x, y is continuous, then it's integrable over a rectangle R. Wait a minute, it's down at the bottom. How do I get off the bottom? There it is. And is equal to the iterated integral in either order, in which the inside integral is a partial integral and the outside variable is treated as a constant. So here it is. Fubini's theorem says to evaluate this limit of the sum of all the rectangular parallelepipeds, you can do this iterated integral. It's an integral with respect to x on the inside, and then an integral with respect to y on the outside, just like that double sum was a sum of a sum. This is an integral with an integral. And so on the, let's see if I can put my hands up here, maybe better. Good one. I hate how machines help you. If I evaluate this integral first with respect to x, and this means a partial integral, right? The notation for the iterated integral means you integrate with respect to x, treating y as a constant, just like the partial derivative was a derivative treating the other variable as a constant. This is an integral treating the other variable as a constant. So I integrate with respect to x and treat y as a constant. Then I evaluate x equals d and a and take the difference if I'm using the fundamental theorem of calculus to evaluate this, right? Then I have just y left in here. I treat it as c, I integrate it as though it's c, then I put y back. And now I've got this integral integrated, comes out of function of y, x disappears, then you evaluate it, d and a and take the difference. Now the outside integral is a function of y only, and I can do that with the fundamental theorem of calculus. So I can now write any double integral as 2 iterated integrals, with the inside one being a partial integral, evaluate both of them with the fundamental theorem of calculus, and that's how we'll do these things. And Fubini's theorem says, furthermore, for these continuous functions, you can do it in either order. You can integrate with respect to y on the outside, x on the inside, or x on the outside, y on the inside. Do this one first, treating x as a constant, and then do an ordinary calculus 1 integral function of x in the second one. So I tell people it's like that terrible joke, right? What is it that you throw away the outside and keep the inside, and then you eat the outside and throw away the inside? You know what that is? Corn on the cob, right? This is like that. You do the inside and then you do the outside, or you do the outside and the inside. And you can do it either order. So that's Fubini's theorem. And now we can use this to actually evaluate some integrals where that limit of the sum was the definition was terrible, right? First, before we actually evaluate one, let's do an approximation, because some of the homework problems are to just do approximations because they're trying to illustrate the concept of a double integral. Suppose I write the Riemann sum for the double integral 2x plus y dA, which would be, what is that in the volume? Double integral 2x plus y. That's the volume below the surface, z equals 2x plus y, right? Which is, what kind of surface is z equals 2x plus y? Stumping you today, huh? Have this on because I'm expecting maybe a call. Sorry about that. if I write that double integral and it's a non-negative function over the rectangle, suppose the rectangle is x going from 0 to 1 and y going from 1 to 3. That's what that notation means. And I take the volume below the surface, z equals 2x plus y. Z equals 2x plus y, maybe you remember, is a plane, right? Ax plus by plus cz equals d is a plane. You can write z equals 2x plus y as a plane. Here's the picture. I'm sorry, it's a little scribbly, but down here, what I'm doing is saying here in the xy plane is the rectangle over which the function is defined. X going from 0 to 1, y going from 1 to 3, right? That's the rectangle, and the xy plane is this one. Now, over that rectangle, here it is drawn in 3 space. I'm going to draw a plane, z equals 2x plus y. How do I know that's a plane? Because equivalently, you can rewrite this as 0 equals 2x plus y minus z. So it's an ax plus by plus cz equals d. With d equals 0, it's a plane through the origin, actually. So I'm taking a plane that actually, if you extended it down, would go through the origin. I'm finding a volume below that plane and over the rectangle. That's x going from 0 to 1, y going from 1 to 3. Right? That's what I'm trying to find with this double integral geometrically. Any questions on that so far? What's the problem? Now, rather than finding the exact amount, I'm going to say, let's estimate it by using a Riemann sum. That's that double sum, right? We could do this. Let's just do it real simple. Let's just make one increment in the x direction, delta x1 from 0 to 1. 2 increments in the y direction, from 1 to 2 and 2 to 3. Now, delta x1 is 1. That's the width of this rectangle. Delta y1 is this width, 1. Delta y2 is 1. So all the rectangles are just 1 by 1. They're just squares. Right? And here it is down here. Here's 2 squares. And what I'm going to do is I'm going to add up the volume of this parallelepiped and add up the volume of this rectangular parallelepiped. And that will estimate the area below the plane. All right. So here's how I do it. I say that the volume is equal to, is approximated by the Riemann sum. K going from 1 to 2 because there's 2 increments in the y direction. J going from 1 to 1 because there's 1 increment in the x direction. F of xj star y, yk star, delta xj, delta yk. That's the definition of the Riemann sum for estimating the volume. Well, if you take this out of sigma notation, we call this, there's only 2 rectangles, so it's just height times length times width of the first one plus height times length times width of the second one. All right, and the length is delta x1 in both of them, but the width is delta y1 in one and delta y2 in the other. It could be different. We define them to be the same. We made delta x1, delta y1, and delta y2 all 1 unit, so it's just 1 and 1 and 1 and 1 is the length and width of each square or rectangle. And then furthermore, to pick the points where we're going to take the height of the rectangle, that's x1 star, y1 star is the point in the rectangle we're going to take the height of the box. And x1 star, y2 star is the height of the second box, right? First increment x, first increment x, first increment of y, and then first increment x, second increment of y. And this will give the height of the first box and the height of the second box, respectively. Where f of xy is the plane, z equals 2x plus y. Now, just for fun, let's do this. Let's pick the midpoint of each rectangle. That's a good place to estimate. We probably, you know, if we do that, take the midpoint, we won't maybe make as much error because part of the time the box will be above the plane, and part of the time the box will be below the plane. It'll sort of cancel out the missing areas. It's better than if I pick an endpoint to evaluate the height. So let's pick the midpoint of each box. Then x1 star, y1 star is the midpoint of this box. X equals 0.5 halfway over, y equals 1.5 halfway up that box, right? And in the second box, if I pick the midpoint, there's pictures like this in the homework. X equals 0.5 is halfway over, y equals 2.5 is halfway up the second box. So that's x1 star, y1 star, x1 star, y2 star, 0.5, 1.5, 0.5, 2.5, the middle of each box. And now I know how to evaluate the sum here. I just take f of 0.5, 1.5, the middle of the first box, and f of 0.5, 2.5, the middle of the second box for the height. Well, height times length times width plus height times length times width, first box, second box. That's what I'm doing on the Riemann sum. Now, what is the height of the box? Well, it's the height of the plane, 2x plus y over it. So I just take 2 times 0.5 plus 1.5. That's the height of the first box. 2 times 0.5 plus 2.5, 2x plus y. So this is the height of the second box. There it is. You just have to grind those numbers. You get 2.5 for this one, right? 1 plus 1.5 is 2.5. 1 plus 2.5 is 3.5. The volume estimate comes out to be 6. So there's the estimated volume under the plane using 2 rectangular boxes and their midpoints to take the height up to the plane above. Any questions on that one? Does it make sense what we did? Here's the picture again if you want to see it. So this is the volume of this first box. This is the volume of the second box, and you add them together and get 6. On the homework, they'll give you like, I don't know, 6 boxes or something. And again, those are completely worthless problems. They're practice getting ready to do this so you understand the concept. But you see how much that's like calculus 1? It's just the definite integral for a function of 2 variables is a double sum limit instead of a single sum limit. All right, now we need to do some actual problems here with the remaining time. Here's the real stuff. Suppose I wanted to evaluate exactly this time the one we just did. The volume over the rectangle, x going from 0 to 1, y going from 1 to 3, below the plane, z equals 2x plus y. How can I do that? We say the volume is exactly, I should do it like the first time. We'll say that the volume is exactly the double integral 2x plus y. I'll have to fix this later. dA over the region. That's how we define the volume, right? Is the double integral. Which this notation here. Where did the pen go? Oh, well. This notation means the limit of the sum of those rectangular parallelepipeds. Right? Get rid of the b here. So volume is exactly equal to this by its definition for a continuous function like a plane. Now, this one by Fubini's theorem can be gotten by an iterated integral, x going from 0 to 1, y going from 1 to 3, iterated. On the inside, you have a partial integral, and on the outside, you have an ordinary integral. Right? So how do you evaluate an iterated integral? You do the one on the inside, treating the other variable as a constant. So I treat x as a constant. When I integrate 2x, I don't get x squared. What do I get? If 2x is a constant, I get that constant times y, right? So 2xy is the partial integral treating x as a constant. Partial integral with respect to y. Integral of y, however, is y squared over 2 because y is the variable. So there's a partial integral of 2x plus y is 2xy plus y squared over 2. Now, by the fundamental theorem of calculus, I can plug in 3 and 1 and take the difference and evaluate the inside integral. Right? So I'm going to plug in 3 and I get 6x. I'm plugging in 3 for y. I get 6x plus 3 squared over 2 is 9 halves. That's the top endpoint. Minus plug in the bottom endpoint. 2 times 1 times x is 2x. Plus 1 squared over 2 is 1 half. So this minus this is the inside integral by the fundamental theorem of calculus. And let's see. I'm missing a page. There it is. But now, 6x minus 2x is 4x, 9 halves minus 1 half is 4. This is just an ordinary calculus 1 integral 0 to 1, 4x plus 4 dx. So when you do the inside integral with respect to y falls out, and you just get an integral of x on the outside. You can use the fundamental theorem of calculus for this. Integral of 4x is 2x squared. Integral of 4 is 4x. Plug in 1 and 0 and take the difference. You get 6 minus 0 is 6. I actually got the same number. That estimate, just by luck, was exactly the same number. Actually, not exactly luck. Can you get an idea how I managed to get an exact number on the last one? This is the beauty of picking the midpoints for taking the height of the function. If you take and estimate the area below a plane and use a rectangular box that's taken at its midpoint, maybe the plane comes up like this. The volume that you This with below the plane that's over the box here is exactly canceled by the volume you overestimate on the other side of the plane below the box, so that you make canceling errors. You miss this area below the plane over here, volume, I should say, below the plane, and you add this volume over here above the plane, and they exactly cancel if you take the midpoint of the rectangular box to get its height. And so it turned out that we just made a lucky choice of where to take our heights of the boxes. When you're taking volume below a plane, you can get exact results by picking the midpoint. But in general, you won't get so lucky and get the exact volume. The Riemann sum will give you an estimate. This double integral is how we define the exact volume, and Fubini's theorem is the way we can do it, because it allows us to use fundamental theorem of calculus. Okay. Well, one last problem here for today, and we'll finish this section. How about that? And try the homework on it. I don't think this section is too hard. You just have to get used to doing those Riemann sums and evaluating these double integrals by Fubini's theorem over a rectangle. In the future, we won't necessarily have a surface that's over a nice, easy thing like a rectangle. That'll be next time. But for now, this section, we'll just say over a rectangle. And suppose we want to evaluate the exact volume below a different function, not a plane, but z equals e to the x cosine y, that's over the rectangle R, which x goes from 0 to 1 and y goes from minus pi over 2 to pi over 2. Suppose I want that one. All right? Same piece of paper. There we go. Here is our definition says that the volume, how do I know this is a continuous function, by the way? E to the x cosine y. Calculus 1, cosine y is a continuous function of one variable. E to the x is a continuous function of one variable from calculus 1, right? The theorems carry over. The product of continuous functions is continuous. The sum or difference of continuous functions is continuous. And the quotient of continuous functions is continuous where the denominator is not 0. So this is a product of two continuous functions. We know it's continuous. Therefore, we're going to apply our theorem that says the volume below a continuous non-negative function, right? E to the x is always positive. Cosine y on this interval is never negative. So this product is a non-negative continuous function. The volume is, by definition, this double integral of the function dA over the rectangle. All right? So there's definition of volume, if you like, but motivated by that inscribed and circumscribed concept. Then Fubini's theorem says to evaluate a double integral, we rewrite it as an iterated integral. And we can integrate with respect to either variable on the inside. Let's do y on the inside and x on the outside, just for fun. And so y will go from minus pi over 2 to pi over 2, its limits, and x will go up between 0 and 1, its limits, right? How do we evaluate this? We can do the same thing as before. We can do a partial integral with respect to this one on the inside, and then integrate the function of x on the outside. But I wanted to show you just a couple tricks here on this one. Here's a real common thing people do, even if you don't want to do this, just do it like we did in the last example. You'll see this in books. I don't want you to go, where'd that come from, right? This is a partial integral treating x as a constant, right? If x is a constant, then e to the x is e to the c is a constant, right? So you can pull a constant out, right? Pull e to the x out and put e to the x out here. Now you've got integral from 0 to 1 dx of e to the x. You can't pull it out of this integral because that integral is with respect to x, but you can pull it out of the y integral. This is a partial integral treating x as a constant. Now I've got integral e to the x times this one. And what do I know about this one? If it's a definite integral, I'm going to get a number, right? This is just a number, integral of cosine y from minus pi over 2 to pi over 2. I'm going to take sine y, plug in these two, and take the difference. It's a number. It's the area under the curve. Cosine y is what it is geometrically. If that's a number, a constant, then I can pull it out of this integral, right? So I can now pull this out of here and write it as integral e to the x dx, pulling the dx through, times this integral minus pi over 2 to pi over 2 cosine y dy. So you see the book do that a bunch of times. It's very convenient. Once you're used to this, you just look at this and immediately write this. Just go straight from here to here once you're used to this. Say, oh, I know what that is. X goes from 0 to 1 e to the x dx. Y goes from minus pi over 2 to pi over 2 cosine y dy. You can do that when the inside integral goes over constant endpoints like a rectangle. And you have a product of a function of x times a function of y. So this won't apply in general. It will apply to a specific case where you have a function of x times a function of y, and you have constant endpoints over a rectangle like that. Now, having done that, all I have to do is calculate one for each of these. Integral e to the x is e to the x, right? It's its own integral. Integral cosine y is sine y. Let's put it on the next. And actually, we can do one more tricky thing here. Some of the problems say use symmetry to evaluate these things. If I want to integrate minus pi over 2 to pi over 2 cosine y, you don't have to do this either. I don't know if it makes it easier in this one. That's actually twice the integral from 0 to pi over 2 cosine y dy. Why is that? Because cosine is an even function, right? It looks like this. It's symmetric over the y-axis as an even function. F of minus x equals f of plus x is the definition. So it looks like this. This area from 0 to pi over 2 is exactly equal to area from minus pi over 2 to 0. So instead of integrating from minus pi over 2 to pi over 2, I can go from 0 to pi over 2 and double it. So that's what I'm saying. I'll take double the integral from 0 to pi over 2. Double this area will be this. So that's how I can do this one. Now I'll integrate cosine y as sine y, plug in these 2 points and take the difference. Integral of e to the x with e to the x, plug in 1 and 0 and take the difference. You get e to the 1 minus e to the 0 is e minus 1. Then there's the 2, and there's sine y, plug in the endpoints and take the difference is 1 minus 0. Evidently, the exact volume under this surface, z equals e to the x cosine y, is 2e minus 1. How about that? And you wouldn't get an exact estimate by a Riemann sum. You'd never be able to exactly cancel the areas on this one. So there it is, an exact volume with a couple of tricks in there. And I just want to point out one more thing that's really useful on these, even more useful. Had this been integral sine y from minus pi over 2 to pi over 2, what would I know the answer is immediately? Suppose that was integral sine y instead of cosine y. What's the answer? Oh, I'm stumping you guys today. Oh. Yeah, there you go, good. How'd you get that? Yeah, they cancel out. Here's sine y is an odd function. Over here, it's exactly minus what it is over here. And when you take the integral from minus pi over 2 to pi over 2, the integral over here gives you plus this area, and integral over here gives you minus this area, but they're the same area. So the two minus the area here plus the area here cancels out and you get 0 exactly. So had this been sine y, I just write 0 immediately. I wouldn't have to do the integral. Use that symmetry property that the integral of an odd function from minus a to a, the areas always cancel, and you get 0 for the integral. All right, that's it then. Try the homework on that section, and let me know if you have any problems.